Colleagues, and Malcolm, thanks for taking your time as well to come and contribute to this chapter, your expertise. As colleagues, as you can see, and most of people here already know who Malcolm is. He is currently being employed in an acting role as the senior manager for distribution smart grids. And I know that his area of specialty is power systems resilience. And he's involved, I think, Malcolm, you had a working group, a CIGRE working group that deals with power systems resilience as well. So thanks, Malcolm. I think you can proceed with your presentation.
Thank you, Chair, and thank you for the colleagues for giving me the opportunity to share some of the learnings that we experience, and I would just like to convey the message of, why should we care about utilities really preparing for extreme events and threats. I guess it's a no-brainer after COVID. I always tell a funny story when we have two incidents. We went to Bloemfontein and indicated to Bloemfontein, you need to think about what if you have an earthquake. Bloemfontein said, no, there's no ways we'll have an earthquake. I think 6 months afterwards, the mines collapsed in Malcom, or somewhere close to Malcom, to the point that the building in Bloemfontein had to be evacuated because it started cracking. So yeah, sometimes testing of faith is interesting. So Chair, I think with Marcus' guidance, and once again, thank you for his persistence to get me here. But I would like to share some of the knowledge. I have forwarded the presentation to Marcus. It's quite a few slides, so I'll narrate quite a few issues. So I think the 4 key issues is what we're going to cover is the power system resilience, what's the principle, why it is important for planners, and how does it for anybody else. I think in the process of setting the context, Chair, this is a picture from my brother when he worked in Wall Street, and my brother's wife was quite pregnant, and this is this real situation that happened in Jersey on the day of the Sandy, and utilities never plan for situations like this, and so it is real. It's really happening. And if we look fundamentally the projections just from a insurance company perspective, you can see the climatological, hydrological, all of these type of disasters has gone beyond and is demonstrating it's increasing in intensity, and also demonstrating increase in number of recorded events. If we just look a little bit closer to home, this is an instance for another low impact, low probability event. We look at a situation where Dr. Gaunt, my supervisor, has studied this whole thing called solar storms, and it's another interesting topic. I think Eloise will be quite well aware of this. Kept National Control quite busy of trying to have a response and an opinion about it. And if we look at the rare event happening in the 1980s, a solar storm can significantly increase the DC level and basically go into saturation of the transformers. And we have experienced a transformer in the outskirts, which is Grassridge and Medupi, where you fundamentally has possible damages or deterioration of the transformer. One of the more famous one is the Canadian blackout. And if you look at the probability curves, fundamentally you typically sway towards, on the tail end you tend to ignore those probability because it is so small to occur. However, these events, there's no silver bullet, and NERC and FERC has quoted this thing called black sky or dark sky hazards, and normally linked to these events like natural, space, terrorism, cyber, and pandemic, which is happening now. These are all actual events that will impact. So the question is, how does utilities really address these type of things? And fundamentally, I mean, we need to think about utility resilience a little bit differently as an engineering fraternity, for the simple reason we got a Disaster Management Act, and if it's found as to be punitive, it can be quite punitive in its recourse of if you find negligent. In the Italian case, there was actually incidents where people were thrown in jail for 6 years, and 6 different Italian scientists and government officials has been thrown in jails in 2000 for 6 years due to an earthquake and making incorrect decisions. So I think we just need to start thinking about resilience a little bit differently. I just want to give you a little high-level view. I'm the chair of the Power System Resilience Working Group, under the auspices of CIGRE C2, we've got fundamentally a 3-prong approach to addressing this challenge. One is dealing on the definition, literature review, international survey, which I'm chairing, and as overall chair also, Dr. Matthias, he is responsible for methods, and so I'll share some of their ideas. And Millenroyd as the old PMAPS chairman, he retired quite recently on the 1st of April. There's some critical questions, and you can read through it. I just want to allude to, I was in my previous role, I wanted to expand these questions, and towards the end of the presentation, you will see some questions being unpacked per these different task teams that we've established, and I would have liked some research institutions to get enthralled into this study so that you know, South Africa can contribute to the engineering fraternity as a large in this evolving topic. So what of power system resilience? We clearly see that it's a concept that's growing of importance. There's having interesting debates around it. The thinking of resilience and how to adopt resilience, and the modeling and the studies is actually evolving. I've added 3 studies and case studies at the back of the supporting slides. I think time would not permit us to actually go through that. Moving resilience or resilience thinking is predominantly in the civil engineering world, and that has evolved into the engineering world and into systems resilience thinking. So resilience modeling is suggested on building a power system that is more prepared for extreme events. But the reality of the matter is that the question is what matrices how do you quantify these things? And the normal reliability matrices would not necessarily work. Government is naturally now playing that role of stimulating the market to make sure that utilities are thinking differently. That is happening in the US and Europe quite actively, and in some form within UK, not UK, but in Australia. And so resilience is becoming more and more a factor based on the government expectation of a prudent utility to respond to extreme events. So this is just one of our colleagues, which is Igor. He's from the Army Corps, and there's always been a debate about what's the issue between risk and resilience and security, and I think part of the presentation today will try to unpack that differences that we've suggested. Initially, it just talked about resilient systems, and there is big conferences around resilient systems, and does not necessarily experience interruptions of less frequency, and which is the predominantly reliability. For the duration of interruptions is much smaller, and obviously the impact. And this was some views that were shared from one colleagues. So if we look at the traditional topic around reliability itself, it's traditionally separated into security and adequacy. And if we look at transient stabilities, that's predominantly the stability studies that national control or voltage collapse or frequency response, those are all traditional bread and butter studies conducted by national control. Adequacy is the more steady state studies, and these are the studies that all the fraternity or power system fraternity gets involved. I think distribution is getting more and more in security studies with the advent of distributed energy resources on distribution network, which is going to change the future way of thinking. So once again, I want to suggest I'll put it to you that these are real events. These are events that does occur, and these are events that does threaten our critical infrastructure in its totality. So let's go a little bit deep into the thinking. And one of the big things that we were grappling in CIGRE was to create a distinction between reliability and resilience. The key issue is that the fundamental thing for me is that most of the time when we describe reliability events, it is statistically very nicely described because you've got tons of data to describe that phenomenon. But if you look at 2 or 3 sample points of extreme events that has occurred, which predominantly people call, it's normally a low probability, but however the high impact. It's like saying, what's the probability of a nuclear event happening at Koeberg or a blackout occurring? Very, 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 very low probability and a very high impact. To introduce the thinking into engineering fraternity, we've demonstrated that there's a multifaceted approach required. You need to think about systems. You need to think about how that event has multiple impacts, i.e. load shedding is a clear demonstration how load shedding will impact, i.e. water industry, hospitals and those things, and the cascaded implications and the interconnection between the two. And what are the aspects where we consider? And the reason why we focus on that is to lean towards saying it's much more than just adequacy and reliability. So reliability leans itself towards a reductionist approach, and in the old traditional reliability theory, you will go saying failure effect analysis, and within failure, I reduce this complex circuit into more smaller circuits, and then from there I calculate the failure rate and times it with my mean time to repair, and that will give me some form of and so that's a more reductionist approach per se. So I'll give you an example. A planner will go and say, to solve my problem, I only have one problem, and that's the transformer. Put in another transformer. From a resilience perspective, the approach will be different. We're saying, let's create more interconnected, because actually putting 2 transformers in a location creates a single point of failure. And we've demonstrated that quite a lot. So how do you create your problem and do it in a subform way? So maybe not to spend too much. So why it is a multifaceted approach? It started in ecology and has been adopted as a position of study within a number of fields, and predominantly in the engineering field. The civil around earthquakes and those things has gone significantly adopted this first and foremost before engineering has. In the climate in disaster management, in sustainability, these are all aspects in which we have, and that's exactly why we have multiple definitions, and these are just a few of the definitions. We can give you tons of definitions around what resilience means within these different disciplines itself. So if we go just to break it down and look at the factors or characteristics that was described, this is just a summary of about 8 key references that we've extracted of key features of resilience and different definitions, and we try to describe this when we actually developed this. We eventually did an international survey, and I forgot to add the international survey in here, but we compiled a CIGRE reference paper And it's like herding cats when you try to get all professors with lots of egos together to get down to a position, and eventually got it down after about, I think it was 6 to 8 months, lots of debates and discussions. This has gone into a reference paper in CIGRE eventually. It's gone into the Future Connection journal, and it's also being cited and republished in a different format to all the CEOs across the world as a formal position. And so how does that definition look? There are two parts to the definition. The first part is that obviously the ability to limit the extent of extreme event and the duration of a system degradation following an extreme event. This is then decomposed into, they call it key actionable measures to be taken, and the key issues before, during, and after an extreme event like this. And you'll see there's a description around those. What does it mean that when we talk about it? This is once again unfleshed out a little bit more within the reference paper that you can refer to on the CIGRE website under C4 as a reference paper for CIGRE. So what are the priorities that we focus on when we talk about power system resilience? And I think that the reality is that it's a multifaceted approach. It's not one fit all. From a reductionist perspective, you would say, oh, redundancy, so I'll focus on redundancy. From a resilience perspective, it suggests that you actually need to do multiple, and I will demonstrate some of those type of cases itself. So I think one of the key concepts that we've got the definition down, and here is some interesting debates, if we have academics connected, is the whole issue discussion, conceptual discussions, which create major stress points within our CIGRE group, which is about almost 40 people, and half of them are academics. So the debates are quite full of egos. So the one on the left just describes that we see, at least myself and one of the lead technical advisors, that continuity of supply is really divided into adequacy and security, which really talks about the reliability domain, and separate to that is the resilience. The reason why we separated this two, and that's one thinking, is that resilience also deals not with the known only, but also deals with the unknown, and or NERC calls it the least credible threat or contingency. And C2 has lots of debates about what's the least credible or credible contingencies. One of the two more favorite ones, there's about 5 different models, and we talk about even further in saying that resilience and adequacy, and now we got resilience, and then there's another one saying that maybe we should represent it in the fashion with the 2 circles overlapping and talking about the least credible or known threats you can describe from a risk perspective. There's further debates, and the next debate is saying that when we take this power system resilience definition, can we describe it from an organizational resilience? Because from a holistic approach, you cannot just say you wish all your problems away, and as a planner, I focus on my infrastructure and that's it. And once again, my resilience are sorted out. We are suggesting that there's an holistic approach, and there's lots of definitions around organizational resilience, and then there's lots of definition about infrastructure resilience. And I think C2 is now unpacking the issue around operational resilience itself. So to really cover the entire ambit and different aspects, and currently in the debate, and once again, it would be interesting to see that. So the conceptual discussion around when do we define between risks when we look at reliability and resilience itself, and it's a good illustration just to frame your mind about when you look at probability and impact. We're looking at the ones more on the right-hand side of the quadrant, and top right and bottom right, and that's predominantly traditional resilience approaches covering that way. If you look on the right-hand side, that just shows you if we describe that probability, a high impact, low probability, you look at probability events and megawatt loss, you can see the extreme events is really on the far end of the curve. And if you look at the magnitude of load loss, is significant itself. So it's not necessarily on the more frequent events, because the more frequent events really suffers very low impact. In resilience thinking, there's different matrices, and from here they call it the trapezoid, and this is saying before the incident, after the incident, and it's got. And I think when you do a lot of frequency studies, it leans itself towards describing it in that manner. And I will unpack this a little bit more and in quantifying this going forward. And just figuratively, the way we normally describe it is saying that how do we make a power system stronger, meaning the way your power system responds can be in three different manners to an incident that occurs. One is a combined approach. One is you make it stronger, meaning you fundamentally do not allow that system to be depressed because of an incident happening, or you totally lose the incident, meaning it goes right down to zero, or you actually sponge it in some way. And that's why SVCs and those type of devices are in the system itself. So what does the planner do, and why is it important for planners? So there are certain phases, and that's why we said it's a multi-faceted program or assessment that is being conducted. The first phase is to define your threat, meaning you geographically map that threat against your modeling around saying the path of the wind corridor or hurricanes within the Eastern Cape is predominantly in these directions. So what we then fundamentally do from a threat assessment is saying, where is those data points and how do that touch our electrical infrastructure? The second phase of that study is just looking at if that wind goes in that direction, at what point, at what gust strength of the wind would it result into failure of that structures on that corridor of what it occurs. The third phase is then doing power system analysis and understanding what load is impacted, the normal stuff, loss of load probability, energy not supplied, and all of those things. And then the third one is to look at how do we then, from operational perspective, recovery perspective, modify the system or do something differently so that we can respond to that disaster itself. So just to give you an indication, you've got a risk base and you said your probability is X. We have a tower and we typically have a line. And if anybody can remember, there's a typical diagram borrowed from Dr. Richard Candy. You have the storm moving towards two MTSs. And as that storm approaches that thing, depending on the intensity of that storm, there will be different stress factors on that physical line that we have over there. So what in resilience theory they work on is looking at fragility curves, and fragility curves is really describing the failure of that tower against the storm intensity that actually passes in that path, depending if it's moderate or high. And so in other words, so the wind speed is of that storm passing is 20, 40 or 60, can't forget the units now. And then we consider the conditional value probability. And that seems to be a more prominent way of describing the energy not supplied rather than using the average value itself. So, so the fragility curve is based on probability of failure. And obviously, the more intense the storm is, the fundamentally more probability of that physical line is failing. And I think I've just stressed that. We can then describe that against the different storms and the storm valley. This is an actual study being done a meter per second. And this is for a UK member that they've studied the whole transmission network. And I think part of the case studies that you have described in detail, and also gave you some reference on describing that in detail. And once again, the initial absorption that occurs is a function of the planning you've done prior, and this is why it's important for a planner, is that saying that if we want to arrest, i.e. the number of transformers being failed in the event transformers, lines, or generator disconnecting, we can deploy different infrastructure conditions or supporting things like SVC reactors or whatever special things you want on islanding mode, to actually allow you to ride through that storm. So the conditions that you do, meaning ahead of plan, you can then arrest this from happening. But more important in my mind is, are you containing the incident? Are you coordinating the response? Are you compressing? Are you checking those? And those are very fundamental investment consideration you need to be doing. To give you an argument's sake, we've done studies in the Eastern Cape for all the snow conditions. Eventually, our decision was to more focus on emergency response and recovery, because these networks are so lightly loaded and it is constrained. And we demonstrated, and you'll see in case study number 2 towards the end, you will see some demonstration using heuristic ways of describing the threat itself. And part of your decision making, if you say contain, you need to choose from the suite of resilience power system strategies. Do you resist the thing, meaning you condense it? Do you provide redundancy? Do you provide reliability, or do you response? And this is a typical approach adopted within the UK around responding to extreme events in itself. And if you overlay those strategies against that trapezoid, you will actually see where you need to put your effort in around before redundancies and resistance. You need to resist that storm, and there's many papers that's been written on that. And eventually you'll find a sweet spot. The reality of the matter is that you need to select, are you capacitating, are you bouncing back, are you adapting to the threat, are you maintaining the desired endpoint, are you withstanding the threat? And those are all consideration in the planning domain that you need to be considering. And you can articulate this. Once again, case study 1 and 2 in the supporting slide actually describe using a system domains thinking, saying that, are we focusing on the physical world, information, cognitive, social world? And we, in the resilience team, we've described that. Are we absorbing, preparing, absorbing, recovering, or adapting to that incident that hits that line, depending on the storm intensity, and how would you? So it's not only a planner that we should be doing this. It should be the response team, the OMM team. It's a suite of people that should be actually engaging on this. So this is just an example of one paper, but it is demonstrated in the case study itself. So as a planner, you fundamentally sit back and you ask the fundamental question. If I look at my hazards, they are natural, space, or any of those hazards, what are my objectives I would like to achieve? I would like to contain the incident, coordinate, quickly restore. And how do I optimize my problem? We consider your constraints, your threat, your capex, your consequences. Is it lightly loaded? What's my vulnerability? Do we have sensitive loads beyond that point? And you'll define and optimize your problem to define what your strategies is going to be. Am I going to focus on institutional arrangement, resistance, and all of those type of things? And that's why it's a multifaceted problem statement that you would like to solve in itself. So how do you do this? I think the reality is that if you look at risk in itself, Kaplan described it. Systems exposure and its hazards can be described heuristically. So case study 1 in the supporting slide is using heuristic methods. Case study 3 will focus on probabilistic method, and I think case study 4 2 is focusing on deterministic approach. So I've demonstrated both of those things, asking the fundamental question, what can happen? So what are the scenarios if we're exposed to that threat? 2, if it does happen, what are the consequences and how do we evaluate those consequences that happen? And 3, what are the probabilities known? How likely is this of happening itself? And this is normally a simplistic approach of looking at risk analysis in itself. But once again, the heuristic method, the probabilistic deterministic method is described in those case studies provided. And so once again, we go through these steps, and this is what's Tasting 2 will be unpacking in the future in itself, which is worrying. I've got another meeting at 12. And then you can then break this down and say, what are the resilience capabilities? Do I absorb the issues, adapt? And then what are the strategies that I want to enhance on the far right? I've added some reference papers that you can refer to, and within these papers, I've also written quite a few papers on those. And so, yeah, different methods are adopted, and the CIGRE 2 will be unpacking this. And so the circular approach is what Matthias has put together, and the heuristic approach that we've adopted is on the far right, and that flow is described over there, and you have that papers that can be demonstrated over here. So more work is coming, more understanding on the matrices, methods, and decision making is, and if you're willing to participate, please participate and see if you would like to be a part of the team. And one of the key questions that we did ask in the thing is the fact that we are suggesting is that what methods are being used, and as you can see, most of the countries are swaying towards using conditional probability theories rather than traditional resilience as a method. So in closing, I think a lot of, and once again, this is also Jersey. My brother took a photo of one of the yachts on the side after Sandy. The higher resilience organization knows that we've not seen these things. Have we ever thought COVID would happen? And what is more important for utilities these days is not when it will happen. It's not if it will happen. The question is when, and are we prepared when it happens? So I'm going to leave you with some closing remarks. Is one, the world is experiencing a number of extreme events. We need to be moving towards a more risk-adverse decision approach to provide protection against high-impact, low-probability COVID-1. 2, modern society is so reliant on IE infrastructure. So cross-sectional resilience and trying to find a system-in-system approach is vitally important. And system-in-system theory and introducing it to reliability is another concept that is unpacked even more. If we don't do it, governments in Europe, UK, all of them, and the US is catching up on listing. I know South Africa is normally 10 years behind, and resilience is an emerging topic and being a spotlight for planners and regulators around the world. Power system resilience is an emerging engineering discipline and is evolving, and I really would appeal to any academic link to it that we need to think of how to unpack that in the future. Okay, so resilience is not necessarily reliable, but reliability is one that is not necessarily resilience. So I'll leave you on that note. Thank you, Chair.
Thanks, Malcolm. Are you able to take a question or so? Colleagues, question or two for Malcolm?
From Karen, if I may. Thank you very much, Malcolm. I appreciate the theoretical analysis and the understanding and the appreciation of the need to coordinate the efforts. I just have the comment, properly built and maintained equipment is obviously much more resilient. So just from an Eskom point of view, what are we doing to build up the workmanship needed, the impact, proper tradesman training, and the inspections so that they know how to do the proper inspections. And then the second point is obviously from the planner's point of view, you know, it's difficult because we don't even have the money to build the capacity needed, and we can't even bring any reliability criteria into the network at this stage. So I'm just interested to know how those two elements are taken care of and taken into the discussions.
Yeah, Chair, Karen, thank you for the more difficult questions. I think question number 2, if I may be approached that, I am just as concerned with you. It's actually linked to 1 and 2 that we can build a world-class power system, but if we don't have world-class resources looking after the world-class power system, that is the real problem that Eskom is struggling with. And the quicker that distribution gets out of the quandrum of giving money to the problem child constantly, the better distribution can look after their own networks. And similar to transmission, transmission has to give money away for the stepchild that is spending all the money. So I apologize, I don't really have a theoretical answer for both those questions.
Okay, Malcolm, we will end it here. And thank you so much once again.
Thank you, Chair. Okay, thank you, colleagues.